Okay, we're going to look at parametric relations and inverses. We'll mainly look at inverses. We'll get to parametrics later in this class, but we'll cover them briefly in this section. So we're going to learn about relations that are defined parametrically, inverse relations and inverse functions, and we're going to learn why that some functions in graphs can best be defined parametrically while others are best understood as inverse functions that we already know about. So, first of all, parametric relations. Okay, another way to define some of these functions or relations is with an xy pair that relies on a third variable called a parameter t. So let's look at an example of that. So let's say our xy ordered pair is really, x varies by this function, so to speak, and y varies by this function. So my x and y ordered pair are constantly varying in basically no relation to one another. We can find these points determined by -3, -2, -1, 0. In fact, we can do this on the calculator too, but you can always make a table where you have t, and then you have x, and you have y. So when you look at this, you'll plug in -3, -2, -1, 0, 1, 2, 3, and so on. So when you plug in -3 into x, you get -4. When you plug -3 in for y, you get 11, and so on. -2 gives you -3 here, and here -2 gives you 6. And so on. Now the calculator will do this for you. So in your calculator, if you go to mode and you put your calculator in parametric mode, so it's in function mode right now, but if you scroll down, do parametric. Then when you go to y equals, you're going to see x varies as, and you're going to use x, which will now be t minus 1. You'll see y varies as t squared plus 2. So t squared plus 2. Now, I'm going to go to my table, so I'm going to go to second table set, and I got to start my t values here, it looks like at -3 and go to 3. So I'm going to start it at -3, and we can look at the table then. And that's what they wanted you to copy down. It gives you your x and y order pair. You can take a look at the graph of this as well if you look at your window, and you know, you might want to change your Tmin to like -3 so you can see a little more of this. Tmax, that's fine. And if you look at the graph, it looks like it's a parabola. Looks like these ordered pair will give you a parabola. Now obviously we can change this window more to see a little bit more of it. Maybe go -5 for x, and maybe go or maybe go up for y max to 6 or something, I don't know. But you can see that it is a parabola. If we were to, for example, eliminate the variable, which is what you're going to do in your homework, or eliminate the parameter, what you do is you solve one of these for t and plug it in. So I would add 1 to both sides and get x plus 1 equals t. And I'd plug that in right here. So I'd have y equals x plus 1 in for this t squared plus 2. So it is a parabola. It's a parabola that has been shifted 1 to the left and moved up 2 units, which is exactly what we see when we graph in parametric mode as well. Okay? That's about all we'll do with parametrics for now. But you know, later we will touch on them a little bit more. So we're going to talk about inverses though. Inverse relations is if the ordered pair AB is in the relation only if the opposite BA is also in the inverse relation. So basically, you know, the point AB right here is reflected over the line y equals x and becomes the point BA. So that's the key to inverses, is that basically it switches the domain and range, switches your x and y value, and is a reflection over the line y equals x. That's what inverses are. And that's what this horizontal line test says. Basically, if you have a function like a parabola, it doesn't have an inverse because it doesn't pass the horizontal line test. So that means that its inverse would be a sideways parabola, reflection over the line y equals x, that wouldn't pass the vertical line test. So it's important that if these functions have inverses, they do pass the horizontal line test. All right. So a couple more things then. Inverse functions. If the function is a one-to-one function with domain D and range R, then the inverse function, denoted with this symbol, is the function with domain R and range D. So basically what that says is you take the domain and range of the original function and switch it to get the domain and range of the inverse function. Okay? So let's do an example then. Let's find the inverse function algebraically. What you do is what I do anyway, is I call f of x y, and I switch it with x, so it becomes x equals 2y over y minus 1. Okay. Now I solve for y, because that's my inverse, and I want to get that by itself. So to solve for y, I'm going to cross multiply. I'll get x times y minus 1 equals 2y. I'll distribute the x, xy minus x equals 2y. Then I'll get the y's together, so xy minus 2y equals x. I just move these to opposite sides. Now I'll factor out a y. So I factor out a y, I'm left with x minus 2 equals x. Divide both sides by x minus 2, and there's my inverse right there. Y equals x over x minus 2. Now instead of calling it y, I'm going to call it inverse of x. That's my inverse function. And if you graph them, they'd be reflections over the line y equals x, and the domain and range would be switched. Okay? The inverse reflection principle says what I said before, which points A and B and A are in the coordinate plane, are symmetric with respect to line y equals x. All right, the points are reflections of each other across the line y equals x. All right, let's find an inverse from a graph then. If we graph this cubic function, this thing's been shifted down 4 units, so it looks something like this. Okay, you can find the inverse then by reflecting over the line y equals x. So this isn't going to be perfect, but it looks something like this. It's just a reflection over line y equals x. It is 1-to-1 because both the function and its inverse pass the vertical line test. Okay. The inverse composition rule is a good one too. You can tell if functions are inverses of each other. If you do the composition, you'll get x, because functions undo one another. So if you have a function that does a certain thing, when you evaluate the inverse, it'll undo what the original function did. So you'll just get the value back that you plugged in. Either way. All right. So if we want to verify that these are inverses of each other, we'd have to do f of g of x. And that would give us g of x is the cube root of x minus 2. Now when I plug that in here and cube it and add 2, that gives me x minus 2 plus 2, which just gives me x. So that verifies one part of it. I'd have to do it again though with the opposite, which is g of f of x. So I'd have to do it again and do g of f of x. And that gives me x cubed plus 2 is f of x. Now I have to plug that in here. So that'd be minus 2, and then I have to do the cube root of the whole thing. Alright, that gives me, this cancels, 2 and minus 2. And I have the cube root of x cubed, which is just x. So it checks that both compositions give you x back, verifying that they are indeed inverses of one another. You could graph them if you wanted to, and you can see that they're reflections over line y equals x. Okay. Here's the steps the book gives for how to find the inverse function algebraically. They're good steps. First of all, to know if it even has an inverse, that's a function, you want to check if it's 1-to-1. Stating the restrictions on the domain, it helps to find the domain first because, like we talked about, the inverse is just, you switch the domain and range. Alright, so then you switch x and y, and then solve for y. Get the formula back, stating any restrictions on the domain of the inverse as well. Okay, and we'll do a bunch of examples in the homework, so I hope this helps a little bit for now.